Uh-oh. What are you doing? I'm glad you made it over, Gideon. I thought you didn't have email, and I was like, oh, I should have put this in the chat. But now I think I might need to email John.
So, since you put it in one email, then I was able to forward it to one that I can access here. And so since I have both at once, I can access that email and get both of the links.
Got it. Okay. I'm wondering if John isn't, well, somewhere in the cloud. I'll have to find him. Wonder if that's going to be like in heaven. What cloud are you on? All right, let me figure out how to email John real quick. It's probably going to go to you too, so yeah, just ignore it. So I just emailed him, and you too. This stuff is one of my favorite to do, partial fractions. I saw it hiding at the end of the, in fact, it's the very last lesson of this book. You know, if I wouldn't have looked forward, we would have never made it to 126. Hey, John, you made it? I'm going to work on finishing this partial fraction that we started. Just getting the common denominator on the right side of the equation. And that common denominator is x times x plus 1 squared. So a is only missing x plus 1 squared. I'm just going to write it this way because I have to FOIL it out. B is missing x and an x plus 1. And C is only missing an x to get the common denominator. Simplify. Simplify again, distribute. So we got ax squared plus 2 ax plus a plus bx squared plus bx plus cx. And then I'm going to gather all my x squared terms, which is just a plus b, and then gather all my x terms, which is 2a plus b plus c. There's 3 of them. And then all my constants. So I have an a, and that's my only constant. Now I am going to set my coefficients equal that are in my x squared terms. I have 0 x squared terms on the left. So 0 equals, I have an a plus b as a coefficient on the right. Then I'm going to gather all my x terms. I don't have any on the left, but I have a 2a plus b plus c on the right. And then I gather all the constants. I have a 4 on the left, and I have an a on the right. So a is going to equal 4. No math for that one. And then I use my 2 equations, 2 unknowns. So 0 equals 4 plus b. So b has to equal -4. And then we use those 2 to find c. 0 equals 2 times a plus b plus c. 8 minus 4 plus c. So c equals -4. And so once we have all our a, b's, and c's, we can solve the initial equation, which was integral of 4 over x times x squared plus 1 squared, or x plus 1 squared. And our partial fractions of it is a 4 over x plus b, what's b? -4 over x plus 1 plus -4 over x plus 1 squared dx. So we're looking at 4 ln x minus 4 ln x plus 1 plus so this is going to be integral of -4. Oh, I ran out of room again. Times x plus 1 to the -2. So it's not a simple ln integral. You add 1. Let's see. So it's -1. So we're looking at 4 x plus 1 to the -1. So this is going to be plus 4 x plus 1 to the -1 plus c. So you're going to notice with these type of problems, every time you have your constant over a factor that's not repeated, then you're going to, your simple, it's going to be an ln of that denominator. But then as soon as you have a factor that's repeated, you just do your integral, and it's going to be a different, it's not going to follow the ln rule anymore, or the ln way that we've been used to. But you know how to take the integrals. Is that okay? Is that
Yeah.
valid? Okay. Okay. Yeah, because this is the only tricky part, or the only different part of this problem was that last factor. Oh, in the book they put it 4 over x. It's the same thing. 4 over x plus 1, or 4 times x plus 1 to the negative 1. All right, let's other side. Let's do another one. There's only one more in this. So 120-2. We are taking the integral of x plus 1 over x squared. So we have a squared factor, and then we have a non-squared factor. So to do our partial fractions, we are looking at a over x plus b over x squared. Anytime you have a repeating factor, you have to do it twice. Once, you know, as a single, and then once as a double. And then c over x plus 2. And then we're going to get our common denominator. So our numerators will equal. So a needs to be multiplied by an x and an x plus 2. B needs to be multiplied by x plus 2. And c needs to be multiplied by just x squared. Simplify. X squared plus 2x plus cx plus 2b plus cx squared. Distribute. And then gather all like terms. So we're gathering all our x squareds. We have an a plus c. Gathering our x's. We have a 2a plus b. And then gathering our constants, which is a 2b. And then now we set our coefficients equal to each other. So x squared coefficients, I don't have any on the left. I have an a plus c on the right. My x coefficients, I have a 1. And I have a 2a plus b. And then my constants, I have a 1 and a 2b. And then start solving from the bottom up usually. So b equals 1/2. And then I can use b to solve that middle equation. So 1 equals 2 times a plus 1/2. So 1/2 equals 2a. So a is going to equal 1/4. Divide by 2. So now I got a and b, now I gotta find c. Oh, c is gonna be the opposite of a. So c equals -1/4. And then we integrate. So the integral of x plus 1 over x squared, x plus 2 is equal to the integral of a over x, so 1/4 over x, plus the integral of b over x squared, so 1/2 over x squared, and the integral of c over x plus 2. So 1/4 ln x plus 1/2 let's see, this is x to the negative 2. Negative x to the negative 1. So this is going to be negative 1/2. X to the negative 1. And this one's minus 1/4 ln x plus 2. I think that's everything. Does that seem okay?
Yeah.
Okay, let's get 4 through 6 for practice problems on this. And I'm looking to see if there's anything from 115. There isn't. But let's see what 121 has. We'll just do the same thing. So lesson 121 has 9 and 10. You guys are going to be good at this. 122. I don't see any in 122. Oh, maybe I do. 7 and 8. And then let's look at the last type of partial fractions that you can have. So we dealt with repeating denominators. We dealt with individual factors. The last type of factor to deal with is in lesson 126. So jump over to page 637. So lesson 126. This is when you have a factor in the form of, let's see, well, their example, 4x squared minus 2x plus 2. If you have an x squared, not a repeating factor, but if you have an x squared in here, then to get your partial fractions, for that first term, it's going to be ax plus b. So we always do 1 degree less in the numerator than the denominator. So typically we were only having 1 degree in the denominator. It was an x minus 1, x plus 3. And so our numerator was just a, b, and c. Now if we have a 2 degree in our denominator, then that means our numerator needs a 1 degree. Does that make sense? I don't know if you're able to follow that. But, so if this one has 2 degrees, that means I need an x in the numerator. So it's ax plus b, and that's going to be over x squared plus 1. And then plus c over x minus 1. So if it only has 1 degree, you only need 1 constant in the numerator. So whatever, if it's x minus 1, x plus 3, whatever, 1 constant. But if it's x squared plus 1, x squared plus 3, then it's going to be 2 terms. And it's going to be, the first term is going to be an x, and the second term is going to be a constant. So you always have to do 1 less, if that makes sense. So let's look at example 1, 126.1. So we're integrating 6x squared minus 3x plus 1 over 4x cubed plus x squared plus 4x plus 1. So we need to first factor out the denominator. And sometimes it's not obvious, but when I look at this, if I kind of first look at the first two that I have and the last two together, separate, well, together but separately, and I see that like I have a 4x plus 1 over here, and I'm gonna look at these first two and see if there's some way that I can factor it out so that it can be ending up with a 4x plus 1. So if I look at that second term, or these first two, like if I factored out an x squared out of just the first two terms, I'm gonna get a 4x plus 1. And then plus, and I'm just gonna put 4x plus 1. And then the numerator stays the same. Still factoring out the denominator. Now I have it into two terms, but I have the same factor in each term. So I'm gonna pull out a 4x plus 1 out of both of those factors. So 6x squared minus 3x plus 1. So I'm pulling out a 4x plus 1. And then I'm left with an x squared plus, and if I pull out the factor of 4x plus 1, I'm left with just 1. Is that step okay?
Yeah.
Okay. Divide into partial fractions. I have just a degree of 1, so I just have a constant. So a over 4x plus 1 plus, now I have a degree of 2. I'm looking at bx plus c over x squared plus 1. And then I'm going to do the same step that we've always been doing. Common denominator. And so a needs to be multiplied by, x squared plus 1. And then bx plus c needs to be multiplied by 4x plus 1. And then I'm going to go ahead and distribute and FOIL. Oops, I got to FOIL that. 4bx squared plus bx plus 4cx plus c. And then you gather your like terms. So I got an a, and I got a 4b for my x's, or x squared, sorry. And what do I got for my x's? I've got a b and a 4c. And then my constants. I've got an a and a c. Is that the only constants? Yeah. And I'm going to set my coefficients equal to each other of like terms. So x squareds, I have a 6x squared on one side of the equation, and then I have an a plus 4b on the other side. And then my x's, I got a -3 on one side of the equation. What do I have on the other? Got a b plus 4c. And then my constants. I have a 1, and I have an a plus c. I'm going to solve this for a. There's a million ways you can solve these. A is same as 1 minus c. And then I'm going to substitute that into that first equation. And then I'll have 2 equations and 2 unknowns. So my first equation will turn into 6 equals, and then instead of A, it's 1 minus C plus 4B. And then that second equation is negative 3B plus 4C. I can simplify this a little bit more. 5 equals minus C plus 4B. And then I can either use elimination or substitution to solve this. I'm going to substitute. Either way, I have to multiply it somewheres. So I'm going to solve this for B. B equals negative 3 plus 4C minus 4C. And I'm going to substitute that in for B there. So now I got 5 equals negative C plus 4 times B, which is negative 3 minus 4C. Simplify. 5 equals negative C minus 12 minus 16C. So I got 17 equals minus 17C. C equals minus 1. Please tell me C equals minus 1. I got A equals 2. And what is B? B equals 1. So A over 4x plus 1 plus bx plus c. Yeah, I didn't follow quite the book, but if you are following the book, we're 1, 2, 3, 4 lines from the bottom of problem set 126. We just made it to 4 lines to the bottom of 126. I don't know if the book did it a little bit differently or not, but we are, like I said, we're at the last, where it says x minus, well, yeah, they have x minus 1 over x squared plus 1 first, and then the 2 over 4x plus 1. But is getting it to this step okay? Whether you follow however the book did it or keep doing it the same way we've been doing it, or I've been doing it.
Yeah.
So we've always come across, okay, we've always come across where we're getting 2 equations, or 3 equations, 3 unknowns, we find our variables, and then we set up our integral. So I'm gonna flip my page and start with that integral that we have. So we're looking to solve 6x squared minus 3x plus 1 over 4x plus 1, x squared plus 1. And then we partial fractioned it into x minus 1 over x squared plus 1 plus 2 over 4x plus 1. And so now we're just taking these two integrals to find the partial fraction. Obviously, the first version of partial fractions was the easiest. The second one added one step of not using natural log. This one, now we're doing a u substitution to solve. So we need x minus 1 over x squared plus 1. I'm just going to do one of them first, and then I'll do the other one and add them together because I don't have space to do it all. So if u equaled x squared plus 1, du equals 2x. Ah, this is where, yeah, this is where that, we did trig functions, right? Integral of trig functions. This is where the memorization of trig functions comes into play. I'm going to separate this fraction into two separate fractions. I'm going to separate it into x over x squared plus 1 and minus 1 over x squared plus 1. I'm just decomposing my common denominator. So now I have three integrals. One is x over x squared plus 1. And then one is negative 1 over x squared plus 1. And I still have that 2 over 4x plus 1. And I am forgetting my dx's all the time here. All right, to solve this one, I use u substitution. U would be x squared plus 1. Du equals 2x. So 1/2 du equals x dx. Well, I have an x dx, so it's du over u. And I'm going to factor out that negative 1. So I'm at x squared plus 1. This is the one right here that we're going to have to memorize or remember from our trig functions, that the integral of, or the derivative of tangent inverse x was 1 over x squared plus 1. I don't know when we did those, how recent, but it was pretty recent. And then this one is going to be, well, we can take this one right away, 2 ln 4x plus 1. Actually, we're going to do another u substitution. U would equal 4x plus 1. Du is going to equal 4. So 1/4 du equals dx. So that means we're going to be factoring out a 1/4. I don't know if you followed that. So this one's 1/2 ln absolute value of u, which this u was x squared plus 1. This one right here is a trig function of tangent inverse x when you have 1/x squared plus 1. And then this one whittles down to 1/2 4x plus 1 plus c. Once you've done one of them, they're all going to end up in the same form. So like when you do one that has, when you have to do an ax plus b, you're going to end up with one of your trig well, probably the tangent trig function. Does that make sense? Like the very first one that we did, we were always doing a du over u and ending up with ln of something. When we added duplicate factors, we had the same thing. We still had the ln of something, but then we also had to do something to this, the integral of something to the -2 power. And then now we're going to be doing the same sort of thing. You know, it just kind of steps up. I don't know, does that make sense? But I'll give you a couple of these to try from lesson 126. If I can find them. I think. Number 6, 7, and 8. But is there any questions on that? Because I see we got like 6 minutes left. I know. What's that?
I think it's good.
Okay, I was gonna say, I know I went over quickly the integration of these. In fact, I did a lot of it in my head and then came back to it. But so yeah, integration by parts. Pretty cool.
Yeah.
I think next time, at least when I was looking over it, I definitely want to hit Rose curves, which is lesson 110. Because I want you to know how to be able to do those, or at least be exposed to them. And then probably we'll end up with the solids, shells and washers method. We've already did discs method, and then we're going to do 2 more methods for rotating solids. So as far as I can tell, those are the big hit topics I'd like to still hit with you guys. Sound good?
Yep.
All right. Well, stay safe, and I will see you guys next. Well, not see you guys next week, but I'll talk to you guys next week. All right. We'll see you guys. Bye.
Bye.
Bye.